Okay, well, it's 1:05, so now's as good as time as any to get started. So just to give everybody an overview about what's going to happen. Um, so I'm going to give a quick presentation just to kind of give some motivation for what we're talking about today. Um, Actually, looks like someone else has just come in. That's Brandon. Nice. All right, so before we do anything though, if you'll all join me, I'd just like to pray really quickly um, to get us started here. So I'm going to do that. So, dear God, thank you so much for this beautiful day that you've made. Thank you that we're alive and that we get to be in your presence together. God, I pray uh, a- as we do this talk, we do this discussion. God, I pray that you would equip me, that you would speak through me during this time, and that everybody would be able to walk away with something that they've heard from you. And it's in your powerful name that we pray. Amen. Okay, great. Uh, so what you can expect is most of the time during the presentation, you can stay on mute. If you have a question at any time, feel free to unmute yourself and say whatever your question is. Feel free to stop me during the presentation if to say, can you repeat that? Or if you want me to discuss something further, I'm happy to stop and do that. You can also type your questions in the chat. I'll be able to look at the chat on Zoom. So that's another way to communicate if you prefer to chat. But that's all I have to say really, and we're going to get started. So I'm going to share the presentation now. So if someone could speak up or just type in the chat that they can see the presentation, that would be awesome. So does at least
I can
one
see
person
it.
see it? Okay,
Yay.
excellent. Okay, okay, excellent. So let me get this sharing here. Okay. So presumably now you see the presentation in full screen, yes?
Yes.
Okay, excellent. Thank you. All right. So, welcome everyone to Eternity Meets Infinity. That's the title of this talk. And we're going to explore what eternity is, what the Bible has to say about it, what some esteemed scientists have to say about this topic, and how mathematician thinks about this. So, we are in for a packed schedule. And the first thing I'd like you to do is I'd like to ask some rhetorical questions. I'd like you to get ready to use your imagination and really bring yourself to these places that I'm showing here. So, the first place, looking up at the starry nights. Now, when was the first time that you looked up in the sky in the dark and you just looked up at the stars and maybe you felt a feeling of wonder, curiosity about what's out there? Maybe you realize that there's something out there that's a lot bigger than yourself, and maybe you felt kind of small, maybe. Um, but the reason why I bring up this kind of memory is it's the first time that we realize, or that we come into one of the first ways that we realize or come into contact with something that's a lot bigger than ourselves. Okay, next up, maybe you've had the opportunity to be on top of a really tall building and you've been able to look out to the horizon. This is another thing. You see the horizon and it seems almost endless, right? I mean, we know now that the world does have an end, or maybe that there's boundaries to the world, but when you're looking out from where you're standing, especially at the top of the tallest point of the building, it looks like it goes on forever. And maybe you get these same feelings that maybe there's something bigger than me out there, or or maybe you have this wonder about what lies on the horizon. Maybe you've been lost in a crowd. This may not be a happy memory, but have you ever been lost in a store or lost, anywhere, an amusement park or something, and maybe you can't find your parents or whatever, and you realize there's a lot of people out there, and there's something a lot bigger in the world than yourself. These are all scenarios um, that I want you to just imagine so we can get our minds ready for what I'm about to talk about. So, here are the central questions that I hope to address today. Maybe not answer exhaustively, but we can at least get started on thinking about these. The first question is, what does the Bible say about eternity? What have esteemed scientists said about eternity? And how does a mathematician think about the infinite? Okay, so first and foremost, I'm going to go through different parts of the Bible and kind of motivate this topic for us. So, interestingly, when I was doing my research before this presentation, I was looking for how many times eternity was said in the Bible. Now, if you look at the King James Version, the word eternity, the English word eternity, is actually there only once, and I was kind of shocked to see this, and it's in Isaiah 57:15. For the high and exalted one, he who inhabits eternity, whose name is holy, says this: I dwell on the high and holy place, but also with the contrite and humble in spirit, in order to revive the spirit of the humble and to revive the heart overcome with sorrow for sin. So, what can we get from this? Well, for one thing, God, this is the He that is referenced here, the exalted one. God inhabits eternity, right? God somehow sits outside of creation. So, if we want a better understanding of what eternity is and what infinity is, then the Bible tells us that perhaps we're going to have to look towards God. Next, in the very beginning of the Bible, we get a glimpse into where God is, right? Genesis 1, verses 1 to 2. Everybody, most people maybe have seen this, but Genesis 1, verses 1 to 2 says, In the beginning, God created the heavens and the earth. Now the earth was formless and empty. Darkness was over the surface of the deep, and the Spirit of God was hovering over the water. So what we can see here is God inhabits a position that sits outside of creation. Now, in the Bible, it talks about how God is omniscient and omnipresent. So not only is he with us, but he is also outside of creation. So that means the natural laws of creation, he's somehow uh, outside of those as well. If you think about perhaps The Sims, for example, right? If anyone has heard of The Sims, then The Sims is a game where, in some sense, you kind of get to play as God, right? You have these characters, and you get to direct their lives, and the point is that you sit outside of the rules of the game, so you could actually change the software of the game to do things that are not possible for these little characters in The Sims, right? So this is how you can kind of think about this, right? God is sitting outside of creation, and so he can change it at will. Okay, so if we want to know more about eternity, we can look towards God to get a better understanding of it. Now, why might we look towards eternity in the first place? Why would we be interested in it? Well, Ecclesiastes 3:11 gives us some insight into that. It says, "He has made everything beautiful in its time. He has also set eternity in the human heart, yet no one can fathom what God has done from beginning to end." So, in some sense, our being drawn to the infinite, to this idea of eternity, is something that is part of us. We are naturally drawn to it. So, the reason why I gave you those scenarios at the beginning is to refresh your memory about the first time that you felt this, the first time where you felt the calling of eternity in your heart. Now, this verse also shows us that somehow humans are limited. we cannot fathom all of eternity, yet we have this understanding and deep desire. We have this deep desire to understand it, and we're deeply aware of this concept of eternity. And last but not least, well, okay, we are interested in eternity. Okay, we know that God inhabits eternity, but why should we care about it, right? I mean, reasonably speaking, why should we care about it? You know, we may be naturally interested in something, but why should we be interested in pursuing it further? Well, in Romans 6:23, the Bible tells us that the wages of sin is death, but the gift of God is eternal life through Jesus Christ our Lord. So the concept of eternity is of personal importance to us rather than just a curiosity. It's rather very grave importance because we can gain eternal life or we can spend eternity separated from God. And as humans, there's very few choices that we make that have eternal consequences. If you look at Ecclesiastes in more detail, you'll find multiple examples, and I'm sure you can think of some examples of things we do that end up being finite, that end up not lasting forever. However, there's one choice we make that does have eternal consequences. So this is of grave importance to all of us. So why did I share all of those? I hope to give you some reasons of where we can look to gain a greater understanding of eternity. I hope to motivate why we care about it, right? Why do we have this yearning towards learning more about the infinite? And last but not least, why is this of personal importance to us? Okay, so we've talked about what the Bible has to say about eternity, and that's by no means an exhaustive or a complete list, but we've touched upon some things that I think are pretty important. Well, let's hear from some esteemed scientists of recent years, you know, the past 100 to 200 years. So this handsome fellow here, his name is Kurt Gödel. So he is a logician, somebody who studies logic, and he's made contributions to mathematics. And he is from Austria, but he actually moved to the United States. So Kurt Gödel was born in 1906 and he died in 1978. And believe it or not, his final resting place, the final place where he was living, is right here in Princeton, New Jersey. He was uh, he was at Princeton University and was doing research there. And what was Kurt Gödel's contribution to mathematics? Well, in particular, it was his incompleteness theorem. So that was a fancy word that probably, or fancy phrase that probably doesn't mean much. But this result is something that he discovered at the tender age of 25 years old in 1931. And what it says is that if we have a sufficiently interesting logical system, right? We have a system that gives us the tools to find truth, then there are going to be things that are true that lie outside that logical system that logical system is unable to prove. So in other words, Gödel's incompleteness result showed that any logical system that a human could come up with is unable to arrive at every truth that exists in this world. And what I hope you can see is you can see the connections to what I've just talked about. Remember, in the Bible, right? The Bible was here way before Kurt Gödel was, right? So actually, you know, maybe you could argue that this is not something new that he discovered, but it shattered the world of mathematics because at the time, Gödel's contemporaries, so there were two people, Alfred Whitehead and Bertrand Russell, they were What was his full name? Kurt Gödel. That's right. Thank you, Matt, for answering. So Kurt Gödel's contemporaries, Alfred Whitehead and Bertrand Russell. So I'll type that in the chat really quickly. Alfred Whitehead, Bertrand Russell. They were working and had actually published a book called the Principia Mathematica. So I'll type that in the chat as well, Principia Mathematica. And this is a very fancy and impressive name, right? But the idea was they were trying to collect all of the tools of mathematics, everything that we had up until that point, and Principia Mathematica was started to be published in 1910. So just after Gödel was born, actually. And their idea was, we can find all the truth. We can arrive at every truth, and we're going to make the most complete mathematical volume that gives us all the tools to arrive at every truth that exists in the world. And this is not an idea that is unique to mathematics. A lot of areas of science, even today, there's this belief held that eventually we will be able to arrive at the truth. You know, we'll be able to explain everything about our universe. And what Gödel proved, and what is clear if you read the Bible, is that that is somewhat of a foolish errand, you know, for lack of a nice way to say it. It is futile, in fact, because we cannot do that just by nature of who we are. And in fact, this was Whitehead and Russell were probably not very happy to hear about this proof in 1931 because it completely invalidated their work, right? I mean, this is thousands and thousands of pages of trying their best to collect everything needed to prove rigorously all the truths that exist in this world. And Gödel basically said that they were wasting their time, which, you know, is if you spend your entire life doing something and someone tells you that what you did was a waste of time, you probably won't be very happy to hear that. But it was true. It was true. And it settled a lot of the issues with mathematics. A lot of the ideas that were still murky and had not been clear, this kind of settled them. Settled a lot of foundational, a lot of the debate about what the foundation of truth and in turn mathematics should be. So you may have never heard of this guy until now, but he has made an insanely large contribution to the foundations of mathematics, and I think more people should know about him. And he actually lived here, you know, lived in New Jersey, which is pretty interesting. So that's Kurt Gödel. And what the takeaway is that if you put this back in the context of thinking about God and looking towards God for an understanding of eternity, what we find is, you know, another intellectual point of view is that, well, you know, I need proof that God exists. We need to be able to prove rationally that God exists. And what Gödel has shown is that that may not be possible, but just because we cannot prove something does not mean the truth value of something is independent of our ability to prove it. That's the summary. The truth of something can be independent of our ability to prove it. Your personal knowledge that God exists is not something that you can really prove to someone else, at least not in a direct way. But it is a truth that you are personally aware of, and your ability to prove it is independent of it being true. So that's just something to think about. Hopefully that made sense. Stop me with any questions if you want me to talk about any of that in any more detail. Okay, And the next scientist I would like to talk about is someone a little bit more famous, likely. So we have Albert Einstein, right? And I'm sure more of you have heard of Albert Einstein, famous physicist in particular, but also was very close to mathematics and actually was a contemporary of Gödel as well. He was alive at the same time and was at Princeton here in New Jersey, Princeton University, at the same time as Gödel. And they actually discussed, they were actually, peers, and they would discuss various things with each other. So it's not surprising, perhaps, that they would have similar ideas when thinking about the infinite or eternity. And so we see this quote from Albert Einstein saying, "The most incomprehensible thing about the world is that it's comprehensible." So let's think about that for a second. Why is it that scientists can, reasonably predict, right? Write down formulas predicting what will happen. Have you ever thought about that? If you've, physics, describing the state of the world and all that, why can we do that with any accuracy at all? Right? I mean, if you think about flying a plane, for example, you can write down a formula or something that shows you that plane can fly. And we have all kinds of things these days, software to show us that a plane can fly. But I think it takes a lot of faith to get on that plane, to put your life in the hands of what at the end of the day is a formula, really, or some principle saying that this thing should be able to fly and you're not going to come back down to the ground and meet an unfortunate end. And so what I would like you to take away from this quote is that the fact that we can understand the natural laws that govern our universe, and there are natural laws that govern our universe. You can look in Genesis again to see more of that. The only way that is possible is because we are made in the image of the person who created those laws in the first place. The only reason we are able to perceive the order behind what should be, intuitively speaking, a chaotic world that should make no sense whatsoever, and often doesn't make any sense whatsoever. The fact that there's order behind that is something that we should not take lightly. And we don't have all the answers, and we never will have the answers. And we can look to the Bible to see that, but we can just observe that. That's why scientific inquiry is interesting, right? If there was an end to the questions, then I don't think it would be that interesting. But the nice thing about science is that if you imagine all of our knowledge as a circle, right, and you have scientists on the edge of the circle who are slowly pushing out human knowledge, right, slowly making advancements, we're getting a deeper understanding. Scientists, theologists, philosophers, all these people who are at the forefront, right? People who we may have heard of and may respect, people who have been uniquely gifted in searching for the truth, are slowly pushing out what we know about the world and thus the creator who put us here. And as that circle gets bigger, you can imagine that the rim, right, the boundary is also getting bigger, right? Our contact with the unknown is also getting bigger. So more questions are going to be raised. And this idea that, oh, one day we'll be able to explain everything is just, without seeming too harsh, it just seems very arrogant if you think about it. Because we are so limited in our understanding that it's hard to, we know that it's impossible, but it's hard to even imagine that somehow we could know everything about the world around us. So that's the takeaway from that. And now we move on to questions and discussion. So I know that initially I said one of the central questions would be, how do mathematicians think about infinity? But I want to stop right now for questions because I know I did a lot of talking, and I would like you to respond with any questions that you have. And then we'll go into the last central question of today's discussion. And I'll stop sharing the PowerPoints. Okay, so please, any questions, comments, anything that has come to mind from this presentation? You can type it in the chat or unmute yourself, anything is fine. But please, any questions?
I think for me, it's more of a comment of it's just interesting to me how humans are fascinated with the eternal and the infinite. Like, no matter how much we've learned about the world, like, there's still that drive within us that, like, wants to know and understand. But then the more we learn, the more we realize that we don't like, the more we realize we don't there's so much we don't know still, and I'm
Mm,
thinking about, I don't know how many of you were here when Dr. Kaida from Princeton came and spoke, but he spent his entire career as a physicist, studying, I think it was some type of matter. And they used to think it like made up 97% of matter in the universe. And then like at the very end of his career, they they learned that it's only like 0.8%. Like, and so he like spent his life thinking that he was like which the studying is still important because it's still teaching us about the world, but like even when we think we understand, there's still so many depths that we don't. So that was something that kind of stood out to me as you were sharing about, especially like the what a lot of like scientists have had to say about it.
thank you. Anything else? Any other questions or things you'd like me to go into more detail about? I know I said a lot of stuff, so it was a lot to take in. So please, if you have any things that you're not sure about, please ask.
This is very interesting so far. Just to give a to let you know how I'm feeling hearing the presentation so far. It's really interesting.
Thank you. And I will, I can share the presentation and the Bible verses and all that later if you'd like to look into those areas in more detail. So yeah, we'll figure out how to do that. But okay,
I have one more question.
sure.
You touched on it a little bit, but from your experience in the math community, how
Mm.
do a lot of mathematicians relate to the concept of infinity in the sense of like, are people in awe of it? Are they like, is it still seen as something incomprehensible, or because we know that infinity exists, do people like think we understand it? Does that make sense?
No, yeah, that is a very good question. And by the way, this whole idea, and so where do I want to start with this? This whole idea of infinity is by no means a settled discussion. Some people will say, okay, well, I don't want to think about it any further, which is fair enough, right? If your concept of infinity works for you and works for the work you do, the idea in mathematics is, well, I don't want to think about what's under the hood. There's definitely some people who have that, idea. As long as what I'm doing um, is reasonable in some sense, then you know the arguments about what exactly is going on under the hood are irrelevant. But yeah, it's by no means a settled discussion, and there's even mathematicians, respected mathematicians, who don't believe in, the idea of infinity, who feel that the idea of infinity is not well defined, um, and that we shouldn't be using it for mathematics. So they actually have a name. They're called finitists. Finitists. I'll type the name in the chat. Finitists. So there's a school of thought that, infinity does not exist, and it's leading us in the wrong direction to consider it as a concept, which is pretty interesting to think about. But there's definitely this idea of awe, like you said. There's definitely this idea of a deep respect for this concept that is very hard to grasp. This whole idea about infinity that I'll show you today is actually one of the first things that you encounter as you start to go into higher level mathematics. So its position in the curriculum, I think, reveals the respect that mathematicians have for it, that this is one of the first things that you should see and think about. I think reveals its importance. And I think it is important to think about. This is one of the first times in math, maybe in a math class that most people have had. And I see your raised hand, Andrew, so I will, answer your question soon. But I feel like most people in the math classes that they've experienced will not have thought much, and, for better, for worse, your teacher may not have mentioned, well, what exactly is going on under the hood? What exactly do we mean by all the things that we are discussing? And I think it's important to at least think about it, once, and if you say afterwards that, okay, well, what we have works for me and I don't want to think about it again, that's your right to do it. But I think it is a worthwhile discussion and it's by no means settled. So hopefully that answers your question. Okay, cool. So Andrew, what was your question?
No, so I just on this topic of infinity, I'm just curious, like, for example, like in some definite integrals, even if infinity is one of the upper or lower bounds, there's a definitive solution. So I feel like even when looking at infinity and utilizing it with a particular like function or mathematical operation, a finite solution still comes from that. So I'm curious, especially for finitists, or the word that you used for them.
Right.
I'm just curious to understand how do they, and I'm curious about again the spiritual implications of like when we look at infinity, like we see finite things that come out of that. So I'm just curious, maybe if you could touch on that. I try to connect both the mathematical and the spiritual, but that's just something that came to mind that I'm just curious about.
Yeah, very good question. So what do I want to say? So you are right. You can have finite things that come out of these tools that are using infinity, as you said. But I guess what it really boils down to in mathematics is you want to have things be well defined, right? You don't want there to be any room for ambiguity, right? That's generally what is strived for in mathematics. And so someone who would find themselves in the finitist camp, and I'm not going to claim to be an expert on their view because, well, I don't hold it, but I know that it exists. And the idea, I think, is that because the concept of infinity itself is ill-defined, in their opinion, and I can give some examples why they would think it's ill-defined. It is not, we should avoid using it in other areas of mathematics, even if they seem to lead to finite answers or to answers that a finitist might accept. So, for example, say you consider what are referred to as the natural numbers or the counting numbers, right? 1, 2, 3, 4, and so on. Now, what we know or that would be used as an example, one of the classic examples of an infinite set, right? And the reason why is there's no largest natural number. Why? Because if you take any number that you can think of and add 1 to it, then that's a larger number, right? So no matter what number we pick, we can always find a larger number. And so that the natural numbers are infinite. But if you think about it, right? I mean, we don't even have names for all of the natural numbers, really, right? I mean, what's the name of the largest number you know? Maybe that would be something to type in the chat, or like, or to say, what's the name of the largest number you know, right? Maybe something like a Googleplex, you know, one of these funny, yeah, a gazillion, right? Exactly. But yeah, Googleplex, exactly. But then, you know, if you claim that's the largest number, you know, gazillion plus 1 is larger, or Googleplex plus 1 is larger. And that really bothers some people, you know. If someone might say, okay, the natural numbers, as you know, the way they would be standardly defined, don't exist. And their challenge to you would be, write down all the natural numbers, right? If it exists, show it to me. So in some sense, you know, if you want to tie it back to religion, or, you know, our faith, a finitist might be someone who, and again, this is just from my surface understanding of, you know, their ideology. So like, you know, if I'm wrong, you know, yeah. But from my surface level understanding, a finitist might be someone who does not accept anything that they cannot tangibly write down or see in front of them. So if you talk about a God, for example, it might be a similar type of person who might say, oh yeah, God exists, well, show him to me, right? So that's the challenge, I think. So hopefully that answers the question. Okay, great. Any other questions along those lines, or maybe along a different line? Or perhaps we're ready to see, well, how do mathematicians think about infinity in a standard way? Actually, I think I can do a poll. Let's do a poll, that'll be fun. So let me see, will it let me do it? Ah, okay. Never mind. Zoom is not letting me do a poll. That's okay though. Okay, in any case, okay, if nobody has any other questions, I will move on. And we're going to discuss, how does a mathematician think about infinity? And before I give my answer, let me flip the question on all of you. So I encourage you to go out on a limb here. You know, it's okay to be wrong, or, you know, whatever. It's okay. Any answer. How would you choose to define infinity? What does infinity mean to you?
I've always thought about it as simply something that never ends. Like it just keeps going forever and ever.
Okay, that's a good definition. I see also undefinable limit, endless bounds, non-stoppable. So it seems we're all having pretty similar ideas. Anyone have a like radically different idea from those ones? Anyone have a different definition?
At the risk of using another word or another description that has like the word un attached to it, or, you know, that is the definition by omission, I guess.
Okay.
Uncountable.
Uncountable. Okay. So that word has a mathematical meaning, but what do you mean by that, Matt?
Like if I tried to count it, I would never be able to. Like there's just no, by the nature of it, no way to count it. no way to put a label on everything.
Okay, so that's an interesting idea. I want to push it a little further, if you don't mind. What about something like sand? Would sand fall under your definition of uncountable?
If you like took a snapshot of all the sand that currently existed, you could count it.
What about time constraints? Like, there's a lot of sand, right? Like, would you live long enough to be able to count it?
I would, if it took me 1 second to count, like between one grain of sand to the next grain of sand, and then it took me half a second to count to the next one, and then half a second to count the next one, I would be able to count it all in a finite amount of time.
Okay, that's true. But that's eventually those periods of time will get pretty small, and I'm not sure I agree that you would be able to do it in that amount of time. I see where you're going, Matt, but okay, what about something that might be a little bit easier? What about the number of hairs on someone's head? Would that fall under anyone's definition of infinite? You can type in the chat or speak out.
I don't think so, because you can define hair. I think unless you're able to kind of define what you're trying to measure. So like you know, eventually if you were to lay out all of the hairs on someone's head, you would eventually be able to count it. Even if it wasn't you, if someone else were to pick up your work, you would be able to get to the end. But if there is no definition to what you're trying to quantify, I don't know if you could consider it infinite, or you could make that finite.
Yeah, okay, so that's a good point. Andrew is saying thinking about regeneration, so do you mind expanding on that a little more?
So I think with that said, like obviously with hair, it continues to grow. Like hairs are continually falling, and then hairs are continuing to be replaced. So that's where I'm curious, as we count the hairs, depending on when you're counting them, like, hey, like one could fall out at one point and then one could come back. One could fall out depending on the head and not be replaced. But that's where I was curious with regeneration about, if the number is continually changing, is there really a finite solution to that? Or is there a consistent constant solution to that particular problem or question?
Right, yeah, so maybe we have to be a little bit careful and say, like, we take a snapshot of someone's head or something, or like one slice of time, and we try to count. Because you're right, yeah, that is a good point. Okay, so why did I ask that question? The first thing is to get you to realize that perhaps our definition of infinity is a little bit suspect or not well formed, and maybe you can empathize with the finitists a little bit. And two, what do I want to say? We have to be careful, right? If we want our definition to not be ambiguous, which is the goal of mathematicians, we have to be really careful about how we choose to say this. So let me ask the question that maybe I should have asked first. What does it mean for something to be finite then?
I would say like definable.
Okay.
Yeah, it has a limit. There are bounds. It stops at a certain point. There's a boundary.
Okay, measurable. It has a limit. There are bounds. Okay. Okay, fair enough. So let me push that idea further. So when you say it has a measurable end via some constraint like time, amount, etc. Okay, so yeah. So in other words, if I'm allowed to make an assumption, probably what most of you imagine is that there's some number associated with, let's say a collection of objects, right? So like a book is finite because there's a number, the amount of pages, that's associated with that book, right? Or the number of items in a grocery store are finite because there's a number associated with the number of grocery items in the store. Does anyone disagree with that? Does anyone say, maybe that's not what I was thinking about? If I mean, when we're thinking of finite?
I mean, as long as there's a perceivable edge to something, it's finite. Like if I had a marble on a table, like, or two marbles on a table, I would know that it's not just one marble on the table because there's a air and then marble and then air and then marble, right? So like two things, there's like a difference between, there's like non-homogeneity between the objects.
Okay, and fair enough. And since, mathematicians like numbers, right? That's what we like. We're going to associate a number with that idea. Okay, so if finite, maybe saying it in the most formal way possible, finite means with the collection of objects, there is a number that we can associate with it such that we can count from 1 up to that number. So for example, the number of pages in a book, if it's a 500-page book, we can count the pages from 1 to 500, and so it's finite. Does anyone have any objections to that definition for now? Okay. So now I want you to imagine a scenario, and perhaps you've heard this from me before, but what would be nice when we're thinking about finiteness and infinity is it would be nice to have some idea of size, right? I mean, if we want to know the definition between the difference between finite and infinite, well, maybe it'd be useful to have some tools to think about what are the sizes of a collection of objects. And by the way, if we know what finite is, mathematicians define infinite as not finite, which, maybe feels unfair, but I guess a positive way of stating it instead of saying not finite is that for any number that we think of, right, and we claim that we can count the objects in the collection from 1 up to that number, there is another element, there's another object that's not any of the other previous objects that we can find. And so that's what infinity means. So like, for example, let me bring the whiteboard up because I think it'll be better with a picture. So let's say we have some objects, right? Now, if something is finite, can everyone see the whiteboard? One person say that, yes, I can see it. Okay, great. So let's say we have this collection here, and it's 5 marbles, right? So since it's finite, we can do this, basically, is what I'm trying to say. And if it's infinite, so let's say we have something, and the ... represents, that it goes on forever. That means if I have something, let's say x, right? Where x is just a number, right? Let's say there's some number that we want to associate with this. What I'm saying is that we can find another one, right? So no matter what we pick, we can always find another one. And so that's how we can give a positive definition of infinity from a mathematician's perspective. So now I'm going to stop to ask if there's any questions, because I know maybe that wasn't the smoothest explanation.
No, that makes sense.
Okay, great. Okay, so now let's think about how can we tell if two different sets are the same size. So now I'd like you to imagine a movie theater, right? Let's say you walk into a movie theater and you look out. How can you tell that there's enough seats for all the people in the theater without counting, right? And the reason why I say that is, the first thing that may come to mind is, oh, well, if we want to see if two things are different, we just count them. And if we get a different number after counting each one, then they're not the same size, right? That seems pretty reasonable. But what about when it's not practical to count, right? We want something where we want a really general tool that we can use at any time and use for any collection of objects, right? So even if it were sand, and obviously we couldn't sit there and count it in a reasonable way, we would be able to use this tool to reason about whether it's the same size as something else. So let's go back to the movie theater scenario. You walk into a crowded movie theater. How do you know there's exactly as many seats as people in that theater? Any ideas?
You can match up a seat to a person.
Okay. So when you're looking out there, I agree with you, you can do that. But when you're looking out there, just from what you see, how can you tell? So using that idea.
Is the movie theater like full?
How can you tell that it's full?
Oh, okay.
How can you tell that there's exactly as many seats as people just by looking at the movie theater?
But it is a full house, like in reality.
I'm asking, how can you tell that?
Okay.
Olu, are you getting to one-to-one functions with this?
Yes.
Okay. So this idea of like, obviously with each, all right, so team, if you have like X being the number of people and Y being the number of seats, you need to have a one-to-one relationship where one person would go in one seat. Like you can't have two people in one seat. So is that what you're trying to get us to generate on of?
Yeah,
is that where you're going with Solu?
Yes, that's exactly the idea. So, so intuitively speaking, if you look at the movie theater and you notice that there's one person sitting in every single seat and all the seats are filled, then you know there's exactly as many people as seats and you don't have to count. So does everybody accept that? Does anyone have a strong objection to that idea? Maybe I should put it that way.
If there's a bunch of people standing and a bunch of empty seats as well, and a bunch of people sitting in seats, would you just like kind of with your finger say, okay, that person in that seat, that person in that seat, that person in that seat, and then look, there's 3 people left over, right? So then more people than seats. Is that like a good extension?
Sure. So what's the idea that I'm trying to do here? Well, let's go back to the whiteboard so I can draw a picture. Pictures make everything better. So let's say, what's the best way to do this? So I guess this is a front view, right? So let's say you have a bunch of seats, or I guess buckets, really. And let's say you have some people in these buckets. Okay, so the reason why you know there's exactly as many buckets as people is because every bucket has a person sitting in it, and no bucket has 2 people sitting in it. So let me look at the chat. Sorry. Ideal movie theater seats, yes, buckets. So what's my point? My point is that there's 2 vocab words that I'd like you to learn. The first one is one-to-one, as Andrew said. So 1, 2, 1. And all that means is that each person has their own seat, right? You don't have two people sitting in one seat. So the following situation would not be 1-to-1. What do I want to do? So each person has their own seat. Okay, and so we're going to do a non-example. So not 1-to-1 would be the following situation. So, you know, maybe it's date night for these two people here. And they decide to sit in the same seat. But that's no good. They're not being 1-to-1. They're not sitting in their own seats. So this is an example of not 1-to-1. And the other vocab word is onto. Onto. So what that means is that every seat has a person sitting in it. And I apologize for my handwriting. Hopefully you can read that reasonably well. So every seat has a person sitting in it. And let's do another non-example, not onto. So let's say we have our movie theater seats once again. And this time, you know, maybe it was a movie that's not well intended and, you know, they just didn't have a person to fill this seat. So there's no person for that seat. And so it's not onto. So you can think of not 1-to-1, meaning that there's more people than there are seats. And not onto means there's more seats than there are people. If it's both 1-to-1 and onto, then each seat has exactly one person. Okay, so that would be this beginning situation. There's enough seats for everybody, and each seat has exactly one person sitting in it. And so we call this a 1-to-1 correspondence. And so the name, which is kind of fancy, but you know, it basically tells you what it is, right? Onto and 1-to-1. And you might say, okay, we've gone through this labor, we've defined these two new words. Olu, why are you telling me about this? Well, this is our tool. This is our hammer. This is our Swiss Army knife. This is what we're going to use to reason about size. So here's a question. Let's say you have the natural numbers, which I'm going to represent with a fancy n. And so that's going to be the numbers 1, 2, 3, 4, and so on, right? The counting numbers, we're familiar with these. And let's consider the even natural numbers. So I'll use a fancy E for that one. And those will be represented by, you know, these are the multiples of 2, right? So 2, 4, 6, 8, counting by 2s, and so on. Are these sets the same size or not? Any ideas? And Matt, I think you know this answer already, so maybe you shouldn't say it.
Shouldn't they be the same? Oh, wait, actually. Say your question one more time.
are the natural numbers and the even natural numbers the same size using the Swiss Army knife of the one-to-one correspondence? So here are the possible answers. Either they are the same size or they aren't the same size. If they are the same size, can you tell me what the one-to-one correspondence is? If they aren't the same size, can you explain why there isn't a one-to-one correspondence? So do you want to try and answer now, Brandon, or maybe Andrew?
So I think an initial thought with this is that if you look at both sets, guys, you're going to have an infinite amount of numbers if they keep going, for either natural numbers or for the natural numbers or for the even numbers. I think a question I have is, Olu, you were talking before about, like, in one of your slides, you had like n and then n plus 2. So I think what I'm curious about here is technically, if you were to compare the natural numbers and the even numbers, you technically have n and 2n. So you can quantify both sets differently by, if you had like starting at n equals 1 n and 2n starting at n equals 1. So that's where, I mean, you have two different functions that you're working with. So I think just interesting insights for the group on that front. Instead of n and n plus 2, you have here n and 2n, base being n equals 1.
Okay. What about intuitively speaking? Intuitively, you know, maybe you're not quite sure how to use what we just talked about to reason with this, but intuitively speaking, are these the same? Just what is your gut feeling on this?
Well, for me, I feel like they're similar in that they both have a locked ratio between the numbers, but the ratio is different. So, like, as far as quantity over time, they're going to be different, but they both have a locked ratio, which is the same.
Okay.
Well, there's something to be said about, like, if you had a finite list of natural numbers, like 1 through 10, and then only took the even numbers out of there, you would have less numbers, right?
Okay.
There's like that intuitive, like, oh, there's less numbers now because I've taken out all the odd numbers. But
so maybe there's, yeah, intuitively speaking, maybe the even numbers should be half as large
there's half as many or something like that.
Yeah, half as large as the natural numbers. Does anyone agree with that? Does anyone object to that? What do we think?
Yeah, intuitively speaking, that's what I would assume. But then both sets stretch on infinitely. So it kind of also doesn't make sense to think that if they're both infinitely large, that they're both different numbers at the same time.
Okay, so somehow maybe our intuition in the finite case is going to fail us if we make things infinite. That's your claim. Anyone else? Or in light of what was more recently said, any other thoughts on this, or are we ready to see what the answer is? Okay. Okay, so actually, counterintuitively maybe, I claim that these two sets are the same size. And the way I'll prove that to you is by showing you what the one-to-one correspondence is. So I actually gave a big hint by drawing these sets these way. I claim that we have the following one-to-one correspondence. For any natural number, it has one and only one seat. And that seat is that number times 2, right? If you multiply two different numbers by 2, there's no way you get to the same seat, right? So that shows that it's 1-to-1. Each of these natural numbers is going to have a seat. And the reason why it's on 2 is that if we take any even natural number, to find the person sitting in it, we divide it by 2, right? If we take half of 2, the person sitting in it is 1. If we take half of 100, the person sitting in that will be 50. So each person has their own seat, and each seat has a person sitting in it. So if you believe that the one-to-one correspondence is a reasonable way to reason about size, you come to the conclusion that these sets are actually the same size, because we can explicitly say what the one-to-one correspondence is. So what's our response to that? Is that acceptable? Do you feel like, perhaps we've gone wrong somewhere? Perhaps we've been led astray? What's our initial reaction to that realization?
It's super counterintuitive because the bottom list increases at twice the rate as the top list. So if you pair up the numbers and the top list and you continue to go further out, so say you get to 100, well, the even number set is already going to be at 200, therefore pushing the bound of that set further out. So if you bring this out to infinity, the natural number list that increases by 1 will be half the quantity, like the end quantity, I guess, of the set below. And I totally get that the function is 1-to-1 because what, like you said, 1 matches up with its x times 2. But it's just mind-boggling because the even set is pushing further out than the end number.
Yeah, that's a good point. The problem is, though, that you're saying n number, and we define infinite sets basically saying that there is no n number.
I know, and that's why it's so confusing.
Right.
This is what makes your mind bend.
Right. So we've put ourselves in a really unintuitive and interesting situation here. From, I don't think we assume that much, right? I think the one-to-one correspondence is a pretty reasonable tool that you would come up with if you sat down and thought about well, how can I count? How can I reason about size without having to count? But now we've come to this conclusion. I don't know. Any other thoughts on this? Is this okay?
I think this is okay. There's no reason we can't just keep taking from a infinite pot, So as we get further and further out into the evens, or as we get further and further out into the naturals, and we need to go double as far out into the evens, it's he doesn't care. Just keep taking,
What were you gonna say, Brandon?
I was going to say, logically, looking at the function, it makes perfect sense, but it's just counterintuitive to us because of what we would normally use to define evenness would be we're looking at the amount of the numbers. So to us, it looks a little confusing when we're comparing 100 being equivalent to 200 from the natural numbers to the even numbers, but it's not really about the amount of the number itself. It's just the amount of items in the set. And I think that's why it's confusing.
Okay. Yeah, that's a good point. And by the way, I mean, this is by no means trivial or anything, right? Maybe by the end of this, you will be in the finitist camp, but But what do I want to say about this? What do I want to say about this in particular? I think this is like one of the first examples you come across where you can feel the limitations of our finite human selves. We are brushing right up against it, right? Intuitively speaking, this should not happen. But now we've come across something that's where our intuition fails us. And in a pretty spectacular way.
I have a question.
Sure.
If the universe is infinite.
Is it?
If it is.
Okay.
Just like the natural numbers and the even numbers, it's not like there's an even number of natural numbers, right? There's an infinite number of natural numbers. So then if the universe is infinite, if we can prove that there are an even number of atoms in the universe, doesn't that mean that it's not infinite?
Well, how do you define it even?
Well, that you can match up, just like we did here, natural, that you can make pairs of like if there's an even number of atoms, then I can pair up every atom. So
okay.
If you can pair up every atom in the universe, it means that it's not infinite. Or if you could pair up every atom and be left with one remaining, it would mean it's not infinite.
So can I maybe rephrase what you're saying? I mean, I think you're presuming when you say even number, in particular, you're focusing, or we should focus on the number part. So you're associating a number with the atoms, right?
Yeah.
Even is a property that is associated with the number in particular.
Yeah.
So yeah, if you assume there's a number of atoms, then you're assuming that, the universe is finite.
Yeah.
In particular.
Or at least that the number of atoms is finite.
Or yeah, at least the number of atoms is finite. That's right. Yeah. Yeah, that's okay. Any other questions or thoughts? I want to do one more example. I think we'll have time for that, but I want to make sure that anything that anybody wanted to say about this has been said. Okay. All right, so I am going to move along then. And okay, so this next one, if you thought this one was really weird and unintuitive, well, you are in for a treat in this next one. So I want to think about how to pose this question. So what if we consider the interval 0, 1? So what I mean by that is all the numbers between 0 and 1, right? So maybe we can represent them as a decimal, like 0. What's the best way to do this? 0.A11, 0.A12, 0.A13, ... And what I should make clear is that each of these is a number from 0 to 9, right? So it's your usual decimal. So for example, if A11 equals 5 and A1 blank is equal to 0 for everything afterwards, then that's just 0.5. Any questions about this notation or any confusion about what I mean by this right now?
Yeah, I think so. If you had A11 is equal to 5, what would be A13, for example?
So if I wanted to write down 0.5, I would make everything after A11 equal to 0.
Oh, I think I get it. So if you wanted to write 0.543, you have to have A sub 1, 2, 3.
Oh, no. So the first number, I don't know, maybe I should put a comma. The first number is the row because I'm about to write more rows. And the second number is the column. So A11 means first row, first column. I put a 5 there. A12 means first row, second column. I put blank there. So in other words, if you wanted to write 0.543, as you said, then A11 has to be 5, A12 has to be 4, and A13 has to be, well, 3. And then everything after that, we'll say A1 blank is going to be equal to 0, right? Because technically there's a bunch of zeros after it, but we don't actually explicitly write that.
Okay, gotcha. Thank you. That makes sense.
Okay, does anyone else have questions about this notation? It's just how I'm choosing to represent a decimal between 0 and 1. Okay. So I'm going to continue. So then the second one in this would be 0.821, 0.822, 0.823, right? Second row, and then first, second, and third column, and it goes on potentially forever. And we continue this process for n, right? So we have 0.8 n1, right? The nth row, where n is just a number, n2, and n3, and that continues forever. Okay, so why am I writing them like this? I'm saying, so what's the point, right? So we have the interval 0, 1. We have a way to represent people in this interval. And my claim is that the natural numbers does not have the same size as the number of numbers between 0 and 1. The natural numbers does not have the same size as the number of numbers between 0 and 1. Does anyone have a question about what I mean by this statement? Okay. So the way we're going to show that this is true is a mathematical trick, or not trick, but a tool called contradiction. So we're going to assume that they actually are the same size. And then we want to show, WTS means want to show, that something goes wrong. I ran out of space. That's supposed to be a G. Okay, let me try that again. So we want to show that something goes wrong. There we go. Okay, so how are we going to do this? Or what's an example of a proof by contradiction? Well, let's suppose you want to prove that the sun will rise tomorrow, right? But you want to do it by contradiction. So I say, I'm going to assume that the sun will not rise tomorrow. Okay, then I wait until tomorrow, and the sun ends up rising. Something went wrong, right? I just found something that was contradictory to what I assumed. And so I can assume that the original claim was actually true, right? So let me try that again. If I want to prove that the sun will rise tomorrow, I assume that it won't rise tomorrow. And then when I wake up tomorrow and see that the sun rose, that's a contradiction to what I assumed. So I can assume that what I was originally trying to prove is true. Does anyone have questions about what contradiction is, or like why it works, or does anyone think that's an unreasonable way to reason about things? Okay. So if you agree that contradiction is a legitimate way to go about this, then we can assume that the natural numbers is indeed equal in size to the interval 0, 1, all the decimals, basically, decimals between 0 and 1. And if they are equal in size, that means that there exists a one-to-one correspondence. So we get some correspondence for free, right? So there's some way to map 2 to this decimal, or 1 to this decimal, 2 to that decimal, and n, right, the nth natural number, to that decimal. And the claim is that there's some one-to-one correspondence that lets us do this. And so what are we going to do? We're going to show that this one-to-one correspondence cannot be on 2. And that will be our contradiction. So let me say that one more time. We're going to show that this is not on 2, right? Because the definition of one-to-one correspondence is that it's one-to-one and it's on 2. And so if we show that it's actually not on 2, it couldn't have been a one-to-one correspondence, which means that these things could not have been the same size. Just as a review, on 2 means that every seat has a person that's going to sit in it. So we're going to create a person, we're going to create a person. No, I'm saying that the wrong way. We're going to create a seat that no person is sitting in. We're going to create a seat that no person is sitting in. And if we do that, we can show that this actually wasn't a one-to-one correspondence after all. Any questions so far about what exactly we're doing?
Could you just repeat that last sentence you said?
Sure. So by way of contradiction, we're assuming that the natural numbers and the numbers between 0 and 1, the decimals, have the same size. Because of that, we get a one-to-one correspondence, right? If 2 things are the same size, then we can write down a one-to-one correspondence. And I've written it down on the left over here, what it should look like. The way we're going to get a contradiction is by showing that this is not on 2. In other words, we're going to create a seat that nobody is sitting in. And so that will show that it's not on 2. And if it's not on 2, it can't be a one-to-one correspondence, which means these things could not have been the same size. Okay. So let's create this seat, this golden seat. And I'm going to call this number b. And b is going to look like 0. What do I want to say? It's going to look like 0.b1, 0.b2, b3, and so on, right? So it's going to look a lot like our A11s, but because there's only one row for b, the number here only refers to the column now, right? So column 1, column 2, column 3, and so on. And here's how we're going to define it. We're going to say bi, right? So the ith column of this decimal is going to be equal to 3 if, what do I want to say? If a I is equal to 5 and 5 otherwise. So let me explain what's going on here. The ith column, we're going to say that it's equal to 3 if the ith row and ith column of one of these numbers on the left here is equal to 5, and we're going to make it equal to 5 otherwise. So what do I mean by this? What I've just done is I've created a number that differs from every single number in this list here, Yeah, no problem, Kristen. Yep, see you. Thank you for coming. And yeah, okay. And okay, so yeah, let me say it one more time. So what's happening here? We're making the ith column in B differ from the ith column of the ith number in this sequence. So in other words, if A11 were equal to 5, then B1 would equal, we said 3. If A22 were equal to, let's just say 9, then B2 would equal 5, and so on. Right? So we're making it different from every single one of the numbers in this sequence in exactly one spot. And because we're doing that, that means that B is not equal to any of these numbers. And if B is not equal to any of these numbers, then that means that it has nobody sitting in that seat. And so we're done. That's the contradiction. But, you know, maybe that is, let me see. Does that make sense? Let me put it that way. Do you understand what this creature B actually is? Okay, so I'm going to assume nobody has questions about what B actually is. So if you believe then that we've successfully defined B, then that means we found a person that has nobody sitting in it. And because we've done that, then we've shown that this is not a one-to-one correspondence, in particular because it's not on 2, which means that the natural numbers and the number of numbers between 0 and 1 do not have the same size. So what have we just done? This is an infinite set, and this is infinite. Right? I mean, you can, the reasoning behind why this is infinite, if you take like 0.5 and 0.6, you can find 0.55, for example, right? And if you take 0.55 and 0.56, well, you can find 0.555. So you can, so this set is infinite because you can always find a new number in between two different numbers. So that's the intuitive explanation for why that's infinite. But the natural numbers are also infinite, which means that we have two different sizes of infinity. And so now we've really gone off the deep end. And by the way, all we've used is our Swiss Army knife of one-to-one correspondence, which is a pretty reasonable assumption, we've agreed, or a reasonable thing to work with. But we've been able to prove not just one really intuitive result, but one really, really unintuitive result. There's different sizes of infinity. And to tie this back into faith, you know, maybe to bring this a little bit more to ground level, you can imagine that even if the universe is infinite, yep, no problem. See you, Emily. Even if the universe is infinite, yep, no problem. See you, Kayla. Thank you. What's the point? Even if the universe is infinite, God can still sit outside of it as an even larger or a different type or kind of infinity. And so that's really the conclusion here. The pursuit of truth, the pursuit of a deeper understanding of the foundations of our existence, all roads lead to God. There's another quote I was thinking about putting in there in the presentation. It was oh boy, I forget you can probably find his name by looking up the quote, but it says the first sip of natural science causes one to be an atheist. But at the bottom of the glass is God. So yeah, that's my conclusion. That's the last thing I wanted to show you. If you have any other questions or if you want to talk about stuff in more detail, I'm happy to do that. But I'm only 5 minutes over